All right, welcome, Nihad. It's Shock Week.
Yes, it is.
I can't believe it's upon us. So I appreciate you spending some time with me. And I know today is Sunday, so today's technically the beginning of Shock Week. We're going to be going live tonight, and but we wanted to take some time. And I know you were traveling abroad. You were over in Egypt, I believe, and other countries too, because it seems like every time I turn around, you're someplace different.
Well, you're always somewhere else the other too. Like, it's not just me, but yes, I spent some time in Cairo, and to your point, yes, I can't believe that it's Shock Week because I recall when you first announced the Shock Week, was it in January or something? I can't remember. We had this live that you went on and you were talking about, this is the plan, we're going to have a Shock Week. And you and I talked over the phone and we're trying to figure out the time and when we'll be meeting and what time in May that we can, I guess, get together, because I was in Egypt for the first 2 weeks. And then when I was back, you were gone. And then when you were back, I was gone. So yeah, it was just interesting that, and then, and hopefully we should see each other in 2 weeks, in under 2 weeks.
That's right. We'll be down in West Virginia for the Pulp and Paper. We're going to be doing a presentation that is very much related to exactly what we're going to talk about today.
Yeah, it's a very similar topic. Not quite the same, but it's the same topic.
Right. So now, for everybody's information, I'm going to be using the NFPA 70, the 2023 edition of the National Electrical Code. We will be referencing the 2024 edition of 70E. So Nihad, why don't you just give everybody a little bit of your background? Okay.
Sure. Yeah. I guess I'm glad to be back. It's not my first time on Tom's channel. It's been an honor. So my name is Nihad Al-Sharif. I'm a professional electrical engineer. I have a master's in electrical engineering. I have an MBA. And my background was more in protection. I started R&D, and then I moved to what my friends call the engineering friends, the dark side. So this would be the product management, marketing, and so forth. I worked for a manufacturer for a few years, and now I'm doing consulting. So I work on my own. I have my little company, which people for some reason can read. It can read the name. It's Monkey Bar Technologies Inc. MNKYBR. Monkey Bar, just one word. That's what happens when engineers become creative.
That's right. And the other thing that happens is they create YouTube channels, right?
Yeah. So this is like the next level of creativity. I'm this much creative compared to you, Tom. But,
I don't know about that, buddy.
Yeah, but this case. So I think pretty much everyone know by now that I'm out of Saskatoon. Like, this is my home, Saskatoon, Saskatchewan, Canada. But I was born in Cairo, Egypt, and my mom still lived there. That's why oftentimes you will find me in Cairo and tell me, Kenny Had is joining from Cairo, Egypt. And I try to go as often as I can to see her. But my home is Saskatoon for me, Canada.
Excellent. Well, thank you and I'm glad we were able to make this happen.
Me too.
We'll probably make this air for tomorrow, and the week is filling out very well, and I've been feverishly making videos. So let's get right to it. So
I have a great lineup.
topic.
I've seen some of your promotion. You have a great lineup of great people, many friends. So I'll be looking forward to watching those videos when they become available.
Excellent. Thank you, sir. All right. So let's talk about our topic today. Is we're going to talk about shock protection, right? So it is Shock Week. So this is going to air tomorrow, the first day of technical sessions for Shock Week.
This is pressure, right? Like, you're going to be the first video. This will be a pressure here.
This is pressure. I'm telling you, Nihad, it's
pressure, man.
Yes, absolutely right. So this is our journey. So Nihad and I, we're just chatting about, okay, how do we want this to flow? So just for everybody's sake, we're going to talk about hazard awareness. Then we're going to move into the impact on the body, and we're going to talk about the aspect of shock itself, meaning the path, the amount of current, and the duration. Then we're going to talk about, once we understand the hazard, we're going to get into risk, and we're going to talk about managing likelihood and severity. And then a part of that, managing severity, is GFCIs and special purpose GFCIs. So we're going to move into understand the differences between the GFCI and the special purpose GFCI. And then we're going to close with, we're going to get into where those technologies are required by the National Electrical Code, and then we'll get into some closing remarks and we'll wrap it up. So, and hopefully we'll be done in about 12 hours. All right.
I'll do it for 24. Okay.
You know how it is, you know?
Yeah, I know. When Tom and I get together, we just lose track of time. It's just like, this is an indication of how much fun we always have when we get together.
Yeah, exactly right. Okay, so let's first focus in on hazard awareness. Now, there are 5 hazards that are identified by 70E. You have shock, you have arc flash, arc blast. There's 4: shock, arc flash, arc blast, and
thermal burn. I think,
thermal burn.
Thermal burn, right? Yeah, something.
That's right.
And this was relatively recent.
Yes,
I think, because initially there were like the 3. I've always been thinking, like, I always thought of the 3 hazards. Actually 2, because arc blast you can think of it as a byproduct of the arc flash.
Yep.
But it's considered a separate hazard, and then the thermal burn is a known.
Yeah. So and the thermal burn, I believe when we're going to talk about that threshold. So it shouldn't be a secret for everybody, but 50 volts, whether it's AC or DC, it really doesn't matter when it comes to 70E. But 50 volts is sort of the identified line of demarcation for the voltage level when it comes to where the shock hazards are. And you know what, Nihad, it just dawned on me. When we talk about the path, the amount, and the duration, that's when we'll understand why 50 volts, right? Okay, so having said that, I want everybody to know that we're going to, as we move into the discussion, what you should be asking in your head is, why 50 volts? I thought we were talking about shock, which is current through the body, yet the threshold for a shock hazard is a voltage value. So that should be an interesting discussion. But if I look at 70E and I look at the definition of shock hazard.
Tom, I think just help me to remember, the 50 volts is the threshold of the minimum voltage limit that we were required to establish an electrically safe workplace, electrically safe work condition.
That is correct. That is correct.
Yeah, so this is the 70. I guess because my point is, we talked about this before the recording, that this is the 70E limit, and part of me thinking it's 30 volts or was 30 volts in Z462, which is the Canadian version of 70E, but I can't remember. So don't quote me on this, but I think it was.
You said Z462.
Z462, yeah. Okay. It's the Canadian version of 70E or equivalent to 70E. But I can't remember. I part of me thinking it was 30, not 50. But I guess my point is, we talked about this before we started recording, that because 50 is the threshold, 50 volts in 70, this doesn't mean that someone is not going to get shocked on lower voltage circuit. Again, it depends on the conditions, and it's not like anything under 50. If it's like, let's say 40 volt. I guess I can think of maybe 24 volts would be a more realistic value.
Sure.
There's still a risk of a shock. It's not as high, but there's still people get shocked working under.
Yeah, and
under cars, or whatever.
Yeah, and we'll get into the discussion of where the 50 volts came to from once we move into the path and the amount and the duration, because that's where that makes sense from a discussion perspective. But what the 70E, and to your point, Z462, you're saying is at 30 volts. 70E is at 50 volts when you don't have to establish an electrically safe work condition. So that presumes that if I'm at, say, 24 volts, AC or DC, that I'm not going to stop the heart from and go into defib for a healthy individual, right? That's sort of the implication by not requiring someone to establish an electrically safe work condition, and that's in 110.2 B of NFPA 70E, right? So if you look at the definition of what 70E calls an electric shock hazard, they say that it is a source of possible injury or damage to health associated with current through the body caused by contact or approach. And we're going to talk about that too, right? So you don't necessarily, depending upon the voltage, you don't necessarily have to touch the energized part.
Yep.
So
Transmission lines, high voltage transmission lines are an example. You get close enough and then you get a shock.
that's
You have to
right.
touch it.
And there was a case of an individual who was exercising a scissor lift. And his job was, whenever you would rent the scissor lift and return it, you would bring it back to the the rental agency, and then he would go back in the yard and just make sure that it was all functional and clean and all that good stuff. And he raised the scissor lift, and because of his proximity to the medium voltage lines or the high voltage lines, they had an arc, basically just from his proximity. He was an arc flashed over, went through his body, down through the scissor lift and killed him. He never came in contact with the lines. It was just he was just close enough to bridge that gap. So that's the definition of shock hazard.
At those high voltages, the voltage is high enough to break the air to turn it into a conductor. It's not dielectric anymore, and the air is a conductor. And he came in touch with ionized air with this,
That's right.
I guess, lift metal apart. Like when he raised the lift, it was just like metal touching. It was like touching the wire, but in this case, touched the air. But the air was ionized because it was not an insulator anymore due to the high voltage of the line. So it's a sad incident, but I mean,
Yeah,
just the old ingredients for a shock was there.
that's right.
We're done.
That's right. So the first step is to recognize the hazard, and 130.4, section 130.4 of 70E is titled Electric Shock Risk Assessment. Now, what it tells you is that an electric shock risk assessment has to be performed, and the first step is to identify electric shock hazards. So based on 70E, you're looking for anything that is greater than 50 volts, right?
Right.
So once you are, now let's talk real quick about the thermal burns. If I have, say I had a 10 volt source or a 24 volt source, doesn't matter, less than 50 volts, and I have a fault, let's say a ground fault, I may not, based on 70E, have a shock hazard, but I definitely could have a thermal burn hazard because current passing through the metal, the enclosure or whatever it's passing through, if I touch it, that's going to generate heat. And if I touch it, I can have a thermal burn. And I think that was the intent of when they introduced the hazard terminology of thermal burn in the first place.
Yeah, probably. I don't remember when it was introduced. I know it was in maybe the last cycle or two, so hasn't been there for a long time. And it just like a toaster, right, or
Yeah.
an electric heater.
That's
You have
right.
enough current, and it just heats up. And if you touch it, you're gonna get burned. You're not gonna get shocked if you touch a toaster, hot toaster, or an electric heater, but you'll definitely get a nice thermal burn.
That's right. That's right. So then the next step in your shock risk assessment. So now we know 50 volts, and if you look in various sections of the 70E, 350.9, 320.3, various sections will tell you when you have to perform the shock analysis or when you have to establish an electrically safe work condition, and they use that 50 volts as that threshold. So if you just searched 70E, you would find multiple references to the 50 volts. So now, the next step is basically in the shock risk assessment, 130.4A general. The first one was identify the electric shock hazards. The second item was to estimate the likelihood of occurrence of injury or damage to health and the potential severity or injury of damage to health. So this gets us into understanding the three key areas, three key to understand, what do you call it? Severity of shock, right? So you have to estimate likelihood and the potential severity. So let's talk severity first. We know that, let's do a quick adjustment here. Move this up just a hair. It was blending too much. So we know that the magnitude of current matters, the path the current takes through the body, and the, what did you call it?
Exposure time. At the time
Exposure
the
time.
person is exposed to the current. I mean, essentially the time that current is allowed to pass through the person's body.
Yeah.
More specifically heart, because it's when it hits when the current is going through the heart, this is the most dangerous condition.
Right. So it's and I had termed it duration, but I like exposure time better. I don't know. It just sounds more sophisticated.
I'm a sophisticated guy. Thank you.
That's
Very
right.
sophisticated.
Yeah. So now for each of these aspects of current through the body, we know that magnitude of current. So let's talk about the amount of current. The path of the current, I can't control the path, right? There's no, I mean, I can't tell you only touch energized parts with your elbow or whatever, because if you accidentally touched something, it's an accident. So it is what it is, right? So the magnitude of current, though, I can't control that necessarily either, because that's basically a circuit. The body has an impedance. The conductors have an impedance. And this is where the voltage comes into play, right?
Yeah. And then the impedance of the body is not constant. It changes because of a lot of other factors. Like, if there's any wet skin, there's moisture, would just drop the voltage down, put the resistance down. If there's the voltage, actually the voltage affects the resistance of the body, because the impedance of the body, I'd rather say, because it's not constant. It's just like they have a capacitive component, so it depends on frequency as well.
Right.
There's a lot of other factors that's like not just, we can just assume that the resistance of the or the impedance of the body is constant. It's not constant. Depends on the situation as well.
Yeah. So this table here is something that we've referenced in the past. This is the ohms of the body, say from a finger touch or a hand holding, finger and thumb grasp. And what I like about this table is it shows you the difference between when your skin is dry versus wet, right?
So I think something to emphasize, Tom, that this is only probabilistic. Like these numbers it's not like set in stone, because if I remember correctly, it was like they talk about the 99 and 95 percentile, maybe, or 90 percentile. I can't remember, it was 90 or 95. So, and this is for healthy people. So someone
Right.
with any underlying, let's say, heart condition or any health issue, the numbers will be very different.
Well, remember, these are just the impedance values. So it's the impedance of the skin or the impedance of the body. So that doesn't necessarily have anything, but it's the one on the right that you're talking
I was just
about.
talking about the right one.
Yeah.
Sorry, the current values. Yeah.
Gotcha. So that image on the right that talks about the 30 milliamps being difficulty of breathing, 20 is respiratory, 50 is fibrillation. That is again, to your point, based upon a healthy human being, right? Or a healthy person. Yeah. Now, what I was looking for here, there was historically, there was a study done where they measured the impedance. This goes back to the 30s. And they measured, here we go. looking for where they measured. They measured the impedance basically by injecting current through the body, and they were able to determine. Here it is. This is your from an impedance perspective, resistance. They did tests through dry skin on the hands, and that they measured that it has a resistance of approximately 40,000 to 50,000 ohms per square centimeter, and then it drops as low as 1,000 ohms per square centimeter when the hands are wet. Now, if you just look at this table, there's the 40,000, okay? And when it's wet, they put down to 4,000, not 1,000, but it depends on, again, how many centimeters and where the measurements were taken. But the fact is, that data is based upon actual measurements that were conducted on human beings to understand the impedance of the skin, etc. And I think it was you, Nihad, that told me. Didn't you tell me that the circuit of a body is really a resistance? Is it in parallel with a capacitor?
It is, yeah. I can pull up the image. I have it, I think, in our paper, but I won't be able to share it now. But it's mainly a resistance, and then parallel with the capacitance. And the capacitance, when we're talking 50, 60 hertz, it's very negligible. So negligible, mainly resistance.
Mm-hmm.
Then, as the frequency starts getting higher, then the capacitance becomes more dominant, and we end up being more capacitive in nature. So the impedance, I guess. The one thing I also remember is the skin. The impedance of the skin plays a big role, because whatever inside the body is very it's constant, like the fluids inside the body and all the power pass in the body. This is very based on the person, right? Like my impedance would be constant, assuming that my skin, neglecting the skin for now, but then Tom impedance will be whatever number it is. But the skin is what gets different because of the moisture level, whether it's wet or dry. And then I believe if I remember correctly, the capacitance has more impact on the skin than the actual body itself. So there's some capacitance internally, but it's all the skin. That's why the skin plays a big role.
Right.
Which, it's just like goes back to this before marinas, right? When people electric shock drowning in marinas, your body is all wet and the impedance is very low, and that tends to come in when there's a leaking boat or some kind, essentially you're swimming into a voltage field,
right?
And just so you have an impedance, and there's voltage across that body, the swimmer's body, and drives current to the person.
Yeah, because remember, you have a voltage potential, and we do step potentials, right? Like in transmission lines and around substations, where if you have a ground fault and current's passing through the ground, you want to keep your feet close together so that you don't have that voltage difference between one foot and another, and that drives current through the body. And to your point, you're somebody swimming in the water. When there's a voltage field in the water, if you are, say, horizontal, and the voltage at your head is different than the voltage at your feet, then you have a difference of potential, which means you'll have current passing through the body.
Yeah, just like a battery, right? Like you have terminals, and you're just closing the circuit. The swimmer's body is closing the circuit. So whatever Tom's just like you just absolutely right to, whatever the potential difference between the head and the toe of the swimmer would just determine how much current will be driven into the person's body. And if this current is high enough, it would cause muscle contraction and even maybe fibrillation. And once a swimmer loses control of his or her muscles, then next thing is they will drown. There's nothing else you can do.
That's right, because we know that from an impact of current through the body, which is another important thing to understand when you're trying to understand when you try to understand the hazard, the impact on the body is, and to your point, it may vary by individuals, but somewhere between zero point 0.5 to 3 milliamps, we have that tingling sensation. And then from 3 to 10, you have your muscle contractions, and then your let go threshold is around 10 to 40. And that's, to your point, your muscles are constricted and you can't move. So if you're in the water, you sink because you can't swim, because your muscles, you can't, they just basically tighten up. And then you lose respiratory paralysis from 30 to 75. And then finally, you have your ventricular fibrillation between 100 and 200 milliamps. So you move up, and as you move as the current moves up, it does more damage to the human body, right? Whether the organs and muscles and all that stuff. So, all right. So,
the point, Tom, I think the point we need to clarify, I know we talked about this maybe the next few minutes, but it's very important that this time, the magnitude that Tom was talking about, assuming that the current magnitude, the exposure of enough time that the person will be exposed to that amount of current enough time to cause this damage. But if this current is cut, the exposure is cut short, like I'll keep using exposure because Tom likes it. So duration of the time is not long enough, then yes, we can prevent those physiological effects, although the current could be in the range that is dangerous, like 50 milliamp or 100 milliamp or something, assuming that the exposure time is not long enough.
right.
And this is where I guess when we talk about controlling right, because we can always control severity of the shock, although the amount of current we can really control because it depends on the circuit and all the impedance of the body and all the other factors, but we can sure control the exposure time or the duration of this current going through the person, which would limit the severity of the shock.
Right.
And this is, I guess, if anyone ever wonders why GFCIs are required to respond really, really fast, because at the end of the day, GFCI is just a ground fault detection method, right? It's just very similar to a ground fault relay. The problem is we cannot tolerate the same current that your motor or pump can tolerate. So if you're protecting a motor or any electric equipment from a ground fault, it's very similar. It's the same, even the same theory of operation detection method like the GFCI uses and the ground fault relay would use to detect a ground fault current. But the difference is the time, because I guess Tom is showing this curve, which determines this is more like an IEC standard, which is a European standard, but it just gives the idea of what the whole what we're talking about. So I guess this is more a visual depiction of the table that Tom was just showing. The guy with milliamp levels. This is more, I guess, visual. So you have zones, right? And the green zone, it's very, I guess, it's very safe. Relatively, you'd feel the tingle, maybe feel the shock. I think it's up to 0.5 milliamp or something. I can't see the curve very well because it's just very small for me. But yeah, so anything under that, you feel something like a really like not major, right? Just like we all get shocked, even like electrostatics, right? Like sometimes there's kind of just you try to change your clothes and then or maybe hold like open a doorknob or something, and then there's like electrostatic. It's very in this range. You feel it, but it's not harmful. Doesn't do anything to you. And then you move up to the current, and then you get this range more like I guess dark orange maybe. And this is more you feel it, definitely feel it, but it doesn't cause that much harm. But again, if you notice, we're not just talking about the x-axis or the current. There is the vertical axis, the y-axis, which is the time. So I guess this curve is showing, I know there's at 5 milliamp roughly, if you extend this vertical line, I know it's not dotted, all the way up, it goes to region B, meets line B, the dotted line on the top, which tells me that anything under 5 milliamp, theoretically, of course, it's not going to happen because you let go as a person, but theoretically, a person can endure an infinite this current, 5 milliamp or less, for infinite of time without having any damage. Now, of course, it's not like I said, because if you're getting a shock, even at this low level current, you let go. Like you're not going to be holding the current or the conductors or touching the equipment that is leaking that current. But theoretically, if this current continues infinitely through the body of the person, it's not going to cause any harm. But the story starts getting a little bit different. The more right you go on the x-axis, so higher current, then you start seeing that this dotted line B, it just has a more of a slope, right? And so if you go vertically for, let's say, for the 20 milliamp or the 30 milliamp line, that the next line that Tom's showing, if you go all the way up, you start transitioning from the orange zone, which has no harm in it, to the light red zone, which this is the muscle, the contraction, and so forth. So the whole idea would try to prevent transitioning into this zone, because this zone is the when you start lose muscle contraction, and maybe you'll still be able, like, we're not going to get into the ventricular fibrillation yet, that the heart is not going into ventricular fibrillation yet, but still it's dangerous enough that we try to prevent getting into the light red zone. And if you notice, the 5 milliamp and 30 milliamp, these are more like the European versus the North American trip levels. So the 5 milliamp plus minus one, we told 4 to 6, 5 plus, like there are different ways of saying it, but this is the GFCI trip level. So we talk about 6 milliamp or 5 plus minus one, but it's the same concept. At that point in time, it doesn't matter how much time the current go through the person, you're still not going to get into any harm. So GSIs are required in North America to trip to provide what they call let go protection, because at this point in time, most people will still be able to let go without needing the power to be interrupted for. If we in Europe, they have a different philosophy, so they use 20 or 30 milliamp, which technically at that time you have some let go issues, would not be able to let go, but the idea is you're going to trip quick enough without getting into the light red zone. So it doesn't provide let go protection, but it sure enough provides ventricular fibrillation protection. So you don't get to the dark red area zone when it's almost guaranteed that you get into the heart gets into fibrillation. So yeah, I guess this is kind of the difference between the two philosophies. North America will provide let go and ventricular fibrillation protection. In Europe, RCD specifically, which is like the European counterpart, or I should say international counterpart of GFCIs, they provide protection. They don't provide let go protection, but they provide ventricular fibrillation protection. So at the end of the day, both devices are designed to trip quick enough to prevent electrocution. But of course, when you are hit with a 20 milliamp or 30 milliamp, the feeling is not going to be as nice, and that's why the GFCI won't wait for till that point. And remember, I think this goes back to the history of GFCI. They started in residential applications. Kids in the house, you have the wife or people who are not necessarily aware of the electric hazard.
Right.
So we try to prevent this from happening. So just like very, very minimum damage. But again, the RCDs still protect people in Europe. And I always joke that the impedance and the current are the same in Europe and North America. Just doesn't mean that it's still the same. Like you get a shock in North America, it's the same feel that you get if you get the shock in Europe. There's different philosophies. And this, I guess, I don't want to get into this yet, but this will be kind of the intro for the special purpose GFCIs, a term that has been it's getting more and more popular in North America in the National Electric Code. That doesn't have it's a personal protection, but doesn't have the 6 milliamp typical Class A GFCI level that we're all used to. This goes up to the 20 milliamp range because of this specific uh, curve that Tom was just showing, which whether we're providing let go protection and ventricular fibrillation protection versus only providing ventricular fibrillation protection like the RCDs devices in Europe.
Okay, so
And I guess the darker areas, like the higher the current, you need less time to get into the dark red area, which is ventricular fibrillation and curve C1, C2, C probability. Between 1 and 2, I think it's less than 5% probability of ventricular fibrillation. Between C1 and C2, it's higher than 5, but less than 50% probability. And then to the right of the last curve, C3, it's almost guaranteed, like more than 50% probability. So it's almost guaranteed that you get into ventricular fibrillation.
So what we're showing on the screen here is that you have higher currents, but higher currents can be can be withstood by the human body for shorter periods of time. So it's like an inverse time current characteristic curve that you would have, say, for a circuit breaker. We just have that similar for how much current can pass. It's almost the damage curve for the body, basically, right? So now
Tom,
I know in this,
point.
I'm sorry, go ahead.
Yeah, go ahead. Sure. I was going to say this is a very good point, Tom, because I know you'll be showing this probably, but the GFCI UL 943 has a curve, and the equation, the time current characteristics of GFCIs are essentially what you're just describing. It's an inverse current.
Yeah. So you have basically a damage curve for the human body, and for higher values of current, shorter values of time are permitted. And to your point, I get into the involuntary muscular contractions somewhere above 5 milliamps for a longer period of time, but as current goes up, that time period comes down, makes it shorter. So the difference between that European RCD type of device is it doesn't have the opening time to prevent let go, right? So they're worried about ventricular fibrillation. And then the U.S. And the Americas markets, where we follow 70E and the National Electrical Code, they worry about the let go thresholds, which is that 4 to 6 milliamps. So this is I really like this slide because it gives you that perspective. A lot of people don't understand that the body can take, say, 50 milliamps or 100 milliamps, but just for a shorter period of time, which gets you directly, to your point, into the curves for the GFCI. And what this one's showing you is your heart fibrillation threshold curve, similar to the previous, right? For higher, and these are in milliamps, and you have your times in seconds. So say upwards of 240 milliamps, the body can handle 240 milliamps, but must be less than, say, 0.2 seconds. But 0.2 seconds is a pretty long time, right? For fibrillation. But for let go, that 220 milliamps has to be cleared before, say, 0.03 seconds. So that green curve on this slide, is the UL limit. And the curve that's lower is your typical Class A GFCI. So to your point earlier on the previous slide, a European type of RCD, that threshold's going to be higher because you're not worried about the green line in those other standards. You're worried about the line up here higher up, which is the fibrillation line. So you have more breathing room, so to speak, for the lack of a better term, right? You have more room for the amount of current that you permit to flow and for a duration of time. So,
and Tom, to your point, the green curve that you're showing, this is the UL curve, Class A, and plus a special purpose as well, plus C, D, and E, for that matters. But this curve is the maximum amount of time, or the maximum exposure time allowed by UL. So you can trip anywhere underneath this curve. That's why you're showing this typical curve, which obviously it's a constant time. And this is what most of the Class A GFCIs that we purchase from like Home Depot, install at home, they don't have a curve. It's just like once you detect the 6 milliamp, you trip at a certain, with certain time delay. I guess we call it instantaneously, but nothing instantaneously. It doesn't have this curve that would say, okay, if I measure 20 milliamp, I'll be tripping quicker than when I measure 10 milliamp, for example.
Right.
And this green curve, the magic number is at 20 milliamp, it's 1 second. This is the maximum time because the equation is 20 divided by I to the power of 1.43. So yeah, if you have 20 milliamp, the maximum time a GFCI is allowed to wait to take the trip, or the maximum exposure time in this case would be 1 second.
Right.
For 20 milliamp. So less than 20 milliamp, I think at 6 milliamp, we're talking maybe 6 seconds or something, or maybe 5 or 6, around 6 seconds. So a lot of time. But again, this goes back to the curve that are in this area. It's almost infinite exposure that it's not going to cause any harm. So 6 seconds, I know sounds ridiculous, but if it's like 5 milliamp or 6 milliamp, yeah, like the person would definitely be able to take 6 seconds of current. And again, at that point in time, because of the low current, most likely the person would let go before the GFCI even feels it, because you'll be like, once you feel the zap, you just let go whatever you're touching. So you don't even need the help of the device, because you're still in the orange area, which was not into the involuntary muscle contraction region. And this is
Right.
when it gets really dangerous, and this is where it gets people stinking, drowning in marinas, because of they just can't swim anymore.
Yeah. So now, to your point, that amount of current flowing through the body is dependent upon the. It's dependent upon the impedance of the circuit, which includes your body and the conductors on the line side, right, that are feeding and supplying the current. So for you to get that low of a current, you would need to have the circumstances of the entire circuit to make that happen. And the voltage potential across the body is what drives that current through your body, right? So I think that's where the basic discussion of 50 volts threshold comes from, is how much voltage do you need to drive through the body? And we have a specific ohmic value of what we perceive as the impedance of the body. And to your point earlier, that's a moving target, right? But we pick a number and we say, okay, if I'm going to say it's 400 ohms, and what voltage do I need to get me around 4 to 6 milliamps, basically? And then that's when I begin my voltage threshold, saying that, well, any voltage above that is going to be hazardous.
And it's interesting that you picked 400 ohms, because UL, when they're testing the GFCIs, they use 500 ohms at the model for the body,
Okay.
which is very conservative, because usually, I think you were showing some numbers. We're talking about the kilo in the kilo, but they're just, because we're testing. So the when we build a circuit to test the GFCI, it's an resistive circuit, right?
Right.
And there is 500 ohms inserted in a circuit, and this 500 ohms is to represent this person in the screen, in the image that Tom's showing on the screen. So again, we know that 500 ohms is very conservative. Most likely the resistance will be higher, but hey, it's safer, right? Because if you insert the higher the resistance, the less amount of current. So it's kind of safer. So we
Right.
try to test at something that is very, very low. Doesn't mean that 500 is the lowest, because if this person is swimming, the resistance could be 200 ohms or 300 because of the water and all the other conditions, right? But the 500 ohms has been the standard in UL testing for GFCIs to represent the human body resistance. Again, we did mention it was impedance, but
Mm-hmm.
because we talk about 50, 60 hertz, 60 hertz for GFCIs when we're testing. So the capacitance is considered as an infinite reactance. It's just
Hold on. Hold on. For some reason, you were muted. I apologize. So let's do this. Yeah, let's do this. Yeah, unfortunately, when I switched to this, so when I get double, it's picking up two audios when I show the screen. So when I show this over here, I get two basically audios. So I have to turn, that's monitor 2. I turned off the wrong audio. So when I flip back over, you were muted. And so let's, I mean, I'm just going to, here's what I'm going to do. I'm going to roll with it. I'm not cutting this out. So everybody's going to be like, but let's go back to this previous discussion. Remember, we had these two.
I don't know what to be lost.
Yeah, I know.
I can
Well,
repeat what I said, but I don't know what we lost.
yeah. So let's talk about this. Let's talk. We know we have the impedance of the body, and we're limiting that circuit, the amount of current flowing through the body, um, and what else did we say? So
I think my comment was when you used the 400 ohms, I said, it
yeah,
was interesting because the value that UL is using for testing GFCIs is
it's
500
500.
ohms. So what they do is, and you may recall from the previous slides, Tom was showing that the impedance or the resistance, I would say, since we're talking 60 hertz, so we're neglecting capacitance because it's almost open circuit. The active capacitance is really high compared to the resistance. So the resistance of the person is in the kilo ohm range.
Right.
So 500 ohms is very conservative. And again, it's better when we're testing, because the higher the impedance of the person or the resistance of the body, it would limit the current more. So it's safer. So UL goes with a conservative number, 500 ohms. But again, that doesn't mean that 500 ohms is the minimum that you can ever get, because again, we're testing in a lab. But when someone is swimming, and when we're talking about like electric shock drowning in marinas, unfortunately, the resistance of the person could be, or the swimmer could be 300 ohms, 200 ohms, whatever the number could be, less than 500 because of the water. And it's not
Right.
just like wet skin, like you're submerged in the water. So obviously there are the different impact. So 500 is a conservative value, but again, the GFCIs were designed to be installed in houses and dry environment. So
Right.
once you get to the marina kind of environment, it's just a different story because now the resistance is much lower, probably more lower than 500 ohms.
Yeah. And how a GFCI functions is it looks at the difference of current. Whatever goes out on that hot wire has to come back on the neutral. And if this is a three-phase, all three hot wires, and if there's a neutral involved, you would put all of those in the donut, but you don't put the equipment grounding conductor in the donut, right? So
Very important, yeah, because you would cancel the whole thing.
exactly. So anytime current flows outside of that path, the difference of current. So whatever goes out on the hot, you subtract from it what comes back on the neutral, and the difference means it's going somewhere else. And if that difference is greater than 6 milliamps, because that's the 4 to 6 milliamps, can't trip less than 4, has to trip after 6. So anything greater than 6 milliamps, it's going to open. And it doesn't know where it went. It just knows I lost current. Current's going somewhere outside of the path, the normal current carrying path. So,
And Tom, this is the very reason that GFCIs have been very, very successful, because, as you and I always said this before, that it's a very unforgiving technology.
yeah,
Like Tom said, if there is 6 milliamp, which is not a lot of current, it's just like 600 six of a thousandth of an ampere, right? If it's missing somewhere, the GFCI doesn't care where it's going. It could be going somewhere in a different, like maybe it's not shocking someone, is going through another circuit or something, but it doesn't matter. The GFCI would trip. And this is the reason I'm saying the reason for the success of this technology. At the same time, the reason that GFCIs, unfortunately for those who are not very educated about the whole situation, getting a bad reputation. And
right.
you always hear nuisance tripping. They trip. They just I can't turn on my lights, or I can't have my power on because of this stupid device. The thing is, it's really, if you think of it, it's doing what it was designed to do. It's seeing very small amount of current missing, that went one way, did not come back the way it should, which means that it's going back to those, because electrons must go back to their source no matter what, right? So if it's not going back to the GFCI in the way that they went, then they're taking a shortcut, or maybe they're taking the highway or whatever, right? So
Yeah.
GFCI doesn't wait; it just drifts. And again, this is the reason has been very successful in protecting people's lives. And at the same time, it's the same reason that they've been getting bad reputation. And Tom knows more than me. A lot of people in the field still to this day hate GFCIs. It's like it nuisance trips, and it doesn't work. It just makes my life hell. Just bypass it. And we've always, see this every year when we're in every cycle for the National Electric Code. It's always push against GFCIs, and there's individuals who are trying not to add new GFCIs to new location. They're trying to take them out of locations that they've been used for years, citing some nuisance stripping reports and things that oftentimes the device is just doing what it was designed to do. There was a problem in the circuit.
Yep.
You know,
So now what we've moved into is talking about managing risk, right? So risk is likelihood and severity. And when we talk about the technologies like GFCI, we are controlling and managing the amount of severity to the body because we're limiting the exposure time or the duration of amount of current passing through the body. Other ways to manage risk with regard to likelihood is when we establish an electrically safe work condition, when we put barriers up, right? And
rubber gloves, right? Wearing rubber gloves when you
wearing rubber gloves,
in a
yep.
circus.
And also just the design of some products, like say a receptacle, and you would think a receptacle has those two holes, right? And you're pushing probes inside of there to energize the circuit, whatever it is that you're plugging into the receptacle. Well, you would say, well, there's these two holes. Why can't I reach my finger and touch it? Well, there are requirements for a distance between the face of that receptacle and the energized parts inside. And then now we have tamper resistant receptacles, which limit the ability to stick things like bobby pins and whatnot into the receptacle itself. So we are reducing likelihood by providing barriers, distance, or through the establishment of an electrically safe work condition, right?
And double insulation too. Like tools are double insulated now, which just minimizes the low. It doesn't eliminate completely, but lowers the likelihood of getting a shock. Because back in the day, tools were metal, and
That's
once
right.
there's a problem, actually it's metal tool, so you can get a shock. It's guaranteed, right?
Yeah. So, and like you say, even if you're doing justified energized work, you should be wearing your rubber gloves, and then also think about the protection of your arms and your shoulders, because you've got to think about the entire, you've got to pop up 30,000 foot and think about everything around you on what am I exposed to, because you don't want to back into something or touch something energized that is on the door that's open, depending upon if it's medium voltage, low voltage, whatever type of equipment. You've got to think about 360 all the ways around you, identify all those hazards from a shock perspective. And we said the threshold for 70E is 50 volts. Z462 is 30.
Not sure about the 30. I think it is. I have to double check, but so don't quote me on this. But I feel that it was 30.
Okay.
Maybe I'm wrong.
All right.
Please, if it's not 30, just don't take my word for it. I have to double check.
All right. Remember, that's what I tell everybody when they watch these programs. Question everything you hear and even more of what you see. So I'm sure everybody is out there is going to do their homework, and then they can leave messages in the chats when they're watching this. So managing risk, likelihood, we know to control likelihood, we're doing all of those other steps. Severity, we get into the discussion of your GFCI and your special purpose GFCI. And we understand the impact to the body from a duration and the amount of current. Now, let's talk about you have this table. I think this came out of the standard.
Yeah, it came out from UL 943C, which is the special purpose GFCI UL standard. Outlier investigation, to be more accurate, because it's not a standard, it's outlier investigation.
Gotcha.
And I think you explained it in one of your programs. I'm a UL friend, but just briefly, outlier investigation is still a document that obtained industry consensus and can be used for listing devices or products. The only difference is between an outlier investigation and standard is an outlier investigation UL document hasn't gone through the ANSI process yet. Like there's some paperwork that they have to do and documentation, and it's like an ANSI process. But this doesn't mean that it cannot be used to list products. I would say the most popular device or product on the market that everyone is aware of and uses is OBC, outlet branch circuit, AFCIs, and the standard, the UL, I guess, documents used to list them is not a standard. It's outlier investigation.
That's right.
It's UL 1699A, if I remember correctly. So it's not a standard.
No.
It's outlier investigation.
Is it A? No. You moved over to AFCI, not GFCI.
Yeah, AFCIs. Yeah. I'm talking about like OBC, right? The OBC, because OBC is very popular. They're very popular. They've been in the standard in NEC for a long time, but actually UL doesn't have a standard for them. an outlier investigation. So special purpose GFCIs, my point is, it's not different. It's nothing different to have a device, a product on the market that's being installed, even a requirement by the NEC, but the UL document is not a standard.
Right.
Right. It's an outlier investigation. So, sorry, I know I went to the AFCI, but I thought of analogy because OBC are more popular than special purpose GFCIs for sure.
Yeah. Yeah. And I just want to make sure that nobody makes the mistake of thinking that an AFCI does anything to do with GFCI.
No. I was just talking about the documents, the names of the documents, outlier investigation, and standard. Because I remember when I first started talking about GFCI, special purpose GFCIs, oh man, it was 2015, I think, back in the 2017 cycle. One of the pushbacks were, this is just, it's not a standard. You can have, the NEC is not allowed or is not permitted to include an installation requirement for a device that is not listed to a standard, a UL standard. And this is kind of my journey of learning. I said, oh, wait a minute, this was not accurate, because it was not an accurate statement, because the OBC, the over outlet branch circuit AFCIs, have been in the code, a requirement, I believe, since 2014.
There are many,
and there's still.
There are many other outline of investigations within the NEC, not just the AFCI, the OBC AFCI. You're picking on that one just because you're aware of it, but I'm just letting you know that there are other ones in there too. So
this is the one
TCF fuse the Cube fuse is another good example.
Right.
Yep. So do you want to explain this slide?
Sure. Yeah. So again, this came out of the UL 943C, and C has nothing to do with the classes or anything. UL has 943A, which is class A GFCI. So they dropped the A. So UL 943, which is very popular. And then UL 943B is the standard for what they call appliance leakage circuit interrupter. So devices used in like your hair dryers and just kind of something. It gets integrated into the LCDI leakage current. AFI.
Not AF.
Not A. Sorry, AC. I can't think of the name of it. 943B appliance leakage. So ALCI. Sorry, appliance leakage circuit interrupter. I forget the acronym. I have to remember what it stands for. So it's appliance leakage circuit interrupter, and as the name suggests, it's very similar to a GFCI, but it's incorporated into appliances, and mainly like the hair dryers and so forth, just to, again, prevent a shock. Someone just drying their hair and don't get a shock or something. So this is incorporated into the cord itself of the appliance. So this is 943B. And when UL proposed this idea of no classes of GFCIs, they had UL 943A and B, so this became C. But has nothing to do with class C, because I know people may think it's a class C thing. No, it's just nothing. So demarcation between the different classes is the voltage of the voltage to ground of your circuit. So if your voltage to ground is less than 150 volt, which is typically what we would see at homes, that's why we did mention the class EFCI, the 4 to 6 milliamp, the one that we're so used to, is mainly installed in residential applications and maybe light commercial, like circuits, 240 volt or less circuits, like 120 volt circuits or whatever. And so the voltage to ground is always less than 150 volt. This would be a class A GFCI. But if your voltage is higher than class and higher than 150 volt, you get into the higher voltages, with the exception of one. If you go to the left, it says no. And then if you have equipment grounding or double insulation required by the code, and I know there's some notes missing, the A is shown in the box. There's some missing notes from this figure, but it just simply says, when equipment grounding is required, which is something that you don't use an equipment grounding conductor for your toaster, for example. But in some applications, when you have an equipment grounding conductor or double insulation required, then you can use class C, although the voltage is less than 150 volt to ground. So I guess my point is class C is interesting because it can go, you can use it when your voltage to ground is 150 volt, higher than 150 volt, lower than 50 volt. This is kind of where it overlaps with class A. But then let's just focus on the higher voltage circuits. Once the voltage is more than 150 volt to ground or higher, you get to ask, let's say, another question. Is your voltage to ground higher than 300 volt? And this is the difference between the 480 volt systems and the 600 volt systems. 600 volt systems are more popular in Canada. I know the US kind of moved away from the 600 volts, so most of the I guess those systems now, distribution systems, are I guess I call them low voltage systems, 480 volt to ground. So if you are less than 300 volt, which is 480 volt systems, you can use a Class C GFCI. But then if your voltage is higher, so this gets to the 600 volt systems. So I guess my point is most cases, most systems in the US, you'll be using Class A GFC, Class C, sorry, GFCI. But if you get to a higher voltage system like 600 volt systems, then you have the decision to make whether to use a Class D or a Class E, and this would depend on the size of your grounding. Class E, let me tell you this upfront, it doesn't exist because it requires what they call ultra half, and the tripping times required by Class E cannot be met using mechanical means of engagement, like a contacts, like a breaker or contactors or whatever, just like something mechanical that opens the circuit. Just like the trip time required is, I think we're talking about like 6 milliamp or something, which is 6 millisecond, which is something we cannot achieve using a mechanical device. So this technology doesn't exist. It's a concept. But then the Class D you can use, assuming that your ground, the equipment grounding conductor is oversized, and there is in one of the appendices in the UL 943C, it kind of shows you how to do it. The whole point is they're trying to limit the voltage across the body to 150 volts or less. So when they have this thing, just like a parallel path, I guess the idea is to make sure that your equipment grounding conductor is oversized so that most of the current would go bypass the person and goes through the equipment grounding conductor back to the source, kind of thing. And this Class D. But for most practical cases in the US or any C applications, it will be Class C. That will be the more dominant.
Okay, so
this
now
is in terms of the voltage classes. Yeah.
So what's the performance? So what's the pickup point for Class C, D, and E? Are they 20 milliamps, 30 milliamps, 40? What are they? Do you know?
Yeah. So this is how you classify the voltages, the classes based on the voltage, but then the performance, like Tom was saying, it's interesting because C, D, and E, it's 20 milliamp. So your trip threshold starts at 20 milliamp. And I know, Tom, there's a curve that we can show that just like you move the start point from 6 to 20 milliamp. Interestingly enough, Class C, there is I guess an exception in 943C that says that you can design Class C to start tripping at 6 milliamp, just similar to Class A. So it can be 6, anyway, from 6 up to 20 milliamp. So what they do is, we talk about Class A, 4 to 6 milliamp. These guys are 15 to 20 milliamp. So you are not supposed to trip less than 15 milliamp. You must trip when it's 20 or higher. Between 15 and 20 milliamp, it's kind of, this kind of the gray area that is 4 to 6 kind of thing.
And that's really, and that's really that's beyond the let go threshold, but before the fibrillation threshold.
Yeah, because again, when I was involved in designing the first of these devices, we call them industrial GFCIs. This is not the term that UL uses, it's special purpose. Right. And I have an issue with the special purpose because maybe it's a good time to discuss this. Special purpose is not a very good terminology, in my opinion, because it has the connotation that they're only used in for special purpose or special applications, which is not true. They can be used in any application that you use a Class A for, provided that the voltage is right. Like you can't install a Class C, let's say, C you can, but D you can install Class D on a 120 volt circuit. You have at home, for example. But Class C you can, because there's an exception there that you can use it, like that's the flow chart is showing less than 150 volts. So if the voltage is right and there's no, I guess, nuisance tripping because of the 6 versus the 20 milliamp kind of thing, you can use a Class C, and pretty much all the applications you can use it for Class A. So special purpose should not imply or that they're only used in special applications. They
You
can be
know,
used anywhere, depending what the code requires them, which is still like a journey, like class A.
it's almost as if they probably would have been better just even in the National Electrical Code, calling it a Class C GFCI, Class D GFCI, and then just specifically say a Class C is permitted, a Class D is permitted, or a Class A is required, or a Class C is required. So if you stuck with the classes, it would probably make more sense, wouldn't it?
And I'm laughing because I think we may have discussed this during the first draft meeting, and this is one of my public comments. Remember, Tom, we made a change in the first draft in the definition of special purpose GFCIs. And I don't know if you know this, but there's no such thing as a special purpose GFCI definition. If you check 943C, this outline investigation, it does not define special purpose GFCI.
Right.
What it defines is Class C, Class D, Class E. So my public comment, hoping to submit once the public comment, which I don't remember when, but I think soon, when the public comment stage opens, will be like, you know what, let's just get rid of the special purpose GFCI definition and call a spade a spade. Class A GFCI, GFCI, comma Class A, GFCI, comma Class C, comma Class D, comma Class E. And what this allows to do is like exactly what you're saying, Tom. If in your application, the installer should be guided to install a Class C, you would tell them install a Class C. Don't tell them special purpose, and they'll be like, which one of these? If they want to install a Class D for whatever reason, because of the voltage levels, just tell them install a Class D. And in the future, if UL decides to come up with a Class K or a Class M or a Class whatever,
right,
it'll be the same thing. Just add the class, and we don't have to worry about the special purpose versus normal, because at the end of the day, they're GFCIs. Which reminds me too, in case someone is wondering, Class B is not on the chart. It's missing. Class B used to be a thing until it was 20 milliamp, which I believe the CDE 20 milliamp came from Class B. Class B was installed in swimming pool light fixtures until I believe 68 NEC.
yeah,
Because before that they had like special kind of GFCIs called Class B, or specifically for the swimming pool light fixtures. But this class is obsolete now. So my point is, if we end up defining classes in the code, then that will be easier for the installer.
So there is a definition for the special purpose GFCI in the 2023 code, and in the changes that were made in the 2026, they got rid of the voltage because of the what you said there. That you can't have a Class C that is less than 150 volts.
Tom, what I meant is the definition is not in the UL standard or outline investigation.
Oh,
it's
yeah.
in NEC.
Gotcha.
Saying, we came up with this definition. If you go back to where this all came from, UL special purpose is the name of the outline investigation. It says special purpose, UL 943C, special purpose. If you go and, the first, like the NEC, usually, I guess, section 3, you have the scope, and then some whatever terminology, and then definition. So the definition part, there's no such thing as special purpose defined by UL. And I had this discussion with our friend, Fred Reyes. I was like, yeah, I'll be doing this, because we argued a little bit and he was not convinced. And I think I convinced him. It's like, in the NEC, we should just go with the definition of classes, because if he's ever introducing new classes, which him and I talked about this, he had some ideas, still kind of in the working. If there's a new class, let's say for marinas or for swimming pools or for whatever specific application, then you can just define the class and tell people use this class in this application.
Yeah, but you could still leave SPGFCI there. You could call a Class C SPGFCI, Class D SPGFCI, and then define those as individual terms, and then you have at least an avenue that you're not changing the title of a standard, but you're still referencing accurately the right terminology.
What I'm planning to do is to say special purpose GFCI. This is a term throwing outwards here. The term collectively used to refer to classes, GFCI classes C, D, and E. And then refer to UL 943C for details. But then I believe we need to include definitions for class C, D, and E, because the elimination of the voltage, as you mentioned, Tom, was because of the inaccuracy, because of C, D, and E, they're not the same. And it's and the one thing I guess we haven't mentioned, class C, D, and E, because of the higher voltage required, the higher trip levels, sorry, require 20 milliamp. They require to have something UL calls ground monitor and interrupt,
Right.
which means that those devices are required to monitor your equipment grounded conductor pretty much. And if your grounding is compromised for whatever reason, those devices are required to trip, which is something that Class A doesn't have. Class A does not monitor your ground. What it does is it just monitors the current going one way and returning the opposite way, make sure that there's what went and on a hot conductor is returning back on the, I guess, the ungrounded conductor, the neutral in this case, whatever.
Yeah.
Or the ungrounded and grounded conductors be the same.
Perfect.
Single phase.
Okay, so let's just let's wrap up our journey here. We talked about the hazard and the hazard awareness. We talked about the path through the body, the parameters to establish the amount of current, and then we understand that the duration makes a difference. We talked about the impact of duration and current on the body. We talked about risk, likelihood, and severity, and the fact that in the severity region, this is when we employ things like GFCIs or special purpose GFCIs. And I think I'm hoping that based upon this dialogue that we just had, that people understand the differences between a GFCI at 4 to 6 milliamps Class A device and your Class C, D, and E special purpose GFCIs. And yeah, we got to do some work moving forward in the 2026 code cycle and beyond. And then finally, we would get into where the next session that we can do, which won't be right now because I'm gonna have to go live here shortly, and then maybe we'll record one tomorrow for later on the week, or maybe we'll go live. We'll have to go live. I don't know. Maybe I'll record later. The next step is to understand where these GFCI devices are required in the code. And I think that's probably going to be left to a different video than this one.
Right. I guess we're out of time because we're planning to share this. Yeah. Hopefully it was a good discussion.
Oh, it was a very good discussion. I know. I enjoyed it because sometimes it's good to have sort of the high level journey and then just noodle around in there and every now and then make a mistake. So I did have you muted for a brief period of time, and there might be some where people are looking at it going, boy, when he went to that screen, I heard like dual Nihads going on. So hopefully that wasn't too bad for everybody who was watching.
Tom decided to censor me. I wasn't just speaking properly. I wasn't behaving properly, and Tom censored me.
Yeah, there you go. We'll just stick with that. Yeah.
Shut up! Don't say that. This is like a family channel.
I love it. Well, beautiful, Nihad. So we've been going about a little over about an hour and 15 minutes. So thank you for taking the time out today. Thanks for joining in on Shock Week. There will be more from you, I'm sure, and I will be going live in the evening, as I will be today at 5 o'clock. So what I'm going to do today is I'm going to use a different tool, and I'll shoot you the link and whatnot. So if you want to pop in and pop back out again, you'll be able to do that. So we'll have a good discussion.
Maybe you just follow up on this discussion, or I know you have a program to share with everyone, which should be exciting. Yeah?
Yes, excellent. All right, thank you, Nihad.
Yes, perfect. Thank you, Tom. Thank you, everyone, and look forward to seeing you during the Shock Week.
Amen. Virtually, yes. All right, thanks, Nihad, and we'll see you hopefully see you in a little bit.
Yeah, you bet. Thank you.
All right, thanks.